Hey, today we're going to be covering the Chapter 1 review questions from the Berean Builders Discovering Design with Physics book. Now, my goal in these sessions is going to be giving you the tools that you need to do the problems yourself. And so at the beginning of many of these review questions is just a list of definitions that you're required to do. And I'm not going to go over these in this session because you have that tool quite easily available yourself just by looking at the book. So we are going to move right along and start with question 2. So this question asks us to indicate the physical quantity that is measured for each of the below cases. And what I want to do first with you is show you something that I have as a study tool to help me with this and all the other problems that have to do with calculations in these review questions. So part of my study strategy is to take the equations and have them on their own sheet and it be something that I can study just by itself. Now, I'm also taking notes on all other kinds of things within the book. Dr. Wile suggests that you take notes on any of the pink sections, all vocabulary, etc., etc. But this is one strategy that I have. Okay, so each equation is labeled with a number in the chapter. I like to add a title to it. So they usually don't have titles. And sometimes they're very simple. It's just the same title as what the first value is in the equation. But sometimes it's a little bit more tricky, and a title will really help you remember what the equation is about. Okay, so for example, I have speed, and that is delta D over delta T. I'm going to define my variables that are letters. So D equals distance and T equals time. With velocity, I have delta X over delta T. Delta T has already been defined up here. T has already been defined, so I'm not going to define it here, but I do put in the V equals velocity and X equals position. Noting that most of the time we're going to be using delta X, which actually means a change in position, which is exactly what the delta means. Delta always means a change in whatever the variable is. And the book gives us an extra term for this change in position and calls it displacement. So I'm going to write that note there because displacement, as you've read through the comprehension check questions, etc., you see that word a lot. I've also highlighted the word velocity because the book tells me that it is a special type of quantity. It is a vector quantity, which means that you have to have a position associated with it, a directionality associated with it. Okay, and then I did the same thing with the relative velocity. Okay, so now as I go through these, my first value is 17 meters per second. All right, so meters is a unit of distance, and seconds is a unit of time. Right, and that just fits right into my distance over time, and that is speed. So I insist on my students writing everything in complete sentences, and the big reason for that is that it requires a little bit higher level of brain functioning when you're doing it, and you're doing two things. You're double checking that your answer is matching what is being asked for, and this one's a pretty simple one, and you're also double checking that your units match what the quantity is that you're stating that your units are supposed to be. Okay, and so my hope with requiring complete sentences for my students is that your brain is having to just do a second glance at these things as you're writing it, instead of just putting out the first number you see and then moving on. Okay, so I will be writing all of my answers in complete sentences here. So 17 meters per second is measuring speed. Okay. 12 inches, well, this is pretty simple. That's a unit of distance. So 12 inches is measuring distance. 1.2 kilometers north. So I have kilometers, which is a unit of distance, and then I have north. And so that is telling me that this is measuring some sort of position, okay, because we have that vector there of north. Okay, so 1.2 kilometers north is a measure of position. We could also use the word displacement here. You don't have to use both, but just want to note that you can use either of those. So 25 seconds, this is another easy one. 25 seconds is a measure of time. And finally, we have 22 miles per hour west. Okay, so we have distance over time, which is very similar to speed, but because we have this west here, that is our vector quantity. So this west makes this miles a position. So this is going to be measuring velocity. So the only difference between speed and velocity is that vector, that location part of the quantity. So 22 miles per hour west is a measure of velocity. Okay, and that is question 2. Now question 3. You ride your bicycle for 5.2 kilometers west and then turn around and ride it 4.3 kilometers east. What is the total distance you traveled? What is the total displacement? So we're being asked 2 questions here. One is distance and the other one is displacement. Okay. And one thing that I am going to suggest that you do is whenever you have these directions or something that is a vector quantity, to remind yourself that you need to pay attention to those directions, do some highlighting, okay? Don't highlight everything in the problem willy-nilly, because then it will be kind of meaningless to your brain. But if it's really important and you need to go back and look at it and double check your answer, highlight something to remind you, okay? So my west, I'm going to designate this as positive, okay? And my east is going to be negative, okay? All right, so my total distance, I'm not going to use these positive and negative. I don't need the west, I don't need the east, okay? Distance is just the total amount written, okay? So for distance, I'm going to say 5.2 kilometers plus 4.3 kilometers, and that equals 9.5 kilometers. for my displacement, that is where the east-west comes into play and my positive and negative, okay? So for my displacement, I just designated west as my positive. So I'm gonna have a 5.2 kilometers. And since this is negative, I'm going to just be subtracting it. You could say plus negative, but I'm just gonna subtract it. 4.3 kilometers. And so my distance, my displacement there is 0.9 kilometers. And notice I didn't put the east and west there, okay? I designated this by the positive and negative while I'm doing this equation, but then I need to add it, okay? So because my answer is positive, that means I'm going to use west, okay? If my answer was negative, then I would have used east, okay? And I'm not going to have the positive or negative as my answer. This is just kind of my placeholder while I'm doing this problem to make it more mathematically easy, and then my answer will take this and convert it to the west or east, okay? So my displacement is 0.9 kilometers west. Now I could stop there, but I'm going to write my answers in complete sentences. So the total distance traveled is 9.5 kilometers, and the total displacement is 0.9 kilometers west. And so after I do that, I'm going to check that I have for the displacement, I have east, west, north, south values, and that what I'm stating is what the question was asking for. So first question was total distance, second question was total displacement. I'm good there, and I can move on. So question 4, suppose you took 925 seconds to make the trip discussed in problem number 3. What was your average speed and what was your average velocity? So this is asking me another 2 questions, okay? So first it's going to be asking me speed, and then it's going to be asking me velocity. And as soon as I see velocity, I'm going to get out my highlighter because that is a vector quantity. And so I'm going to highlight that. Notice there's nothing in this question that says any kind of direction. And so if I don't highlight this, I'm going to have a hard time remembering that, oh wait, I need to add a direction here. So I'm going to highlight that. And so when I put in the answer, I'm going to see that highlight and make sure that I include the direction. Okay. So let's do speed first. Okay. So speed equals distance divided by time. Actually, I'm not going to write that here. I'm just going to refer to this, okay? And if it helps you to write it as part of the answer, that is great. But speed equals distance divided by time, okay? My delta D divided by delta T, okay? So my distance was 9.5 kilometers. And my time is what it gave me, 925 seconds. I'm going to underline that because that's something I'm going to use, okay? And so now I'm just going to simply divide, and we have to keep in mind rules about significant figures with this. So when we are multiplying and dividing, the total number of significant figures of the part of the problem with the least number of significant figures is what we're going to use, okay? So 9.5 kilometers has 2 significant figures. 925 seconds has 3. So our answer is going to need to have 2 significant figures, And so when I do that division, I'm going to get 0.010, and my units just carry over, kilometers per second. Okay. And so this has two significant figures. Everything to the left of the 1 is not significant. Okay, you start the significant figures with the first non-zero number after the decimal place. So 1, 2. And so I'm going to go ahead and write this here so I just don't forget to do it. So the speed is 0.010 kilometers per second. Okay. Now I'm going to do the velocity. And so with the velocity, again, we are keeping in mind the directionality. So with the velocity, we have delta x divided by delta e. Well, we determined delta x in this previous problem. That was the displacement, okay? If we hadn't done that, we would, and we were given this information, we'd have to do that at the top of this equation. But we already have it. So our displacement is 0. And it might actually just go ahead and be a good idea. Delta x divided by delta t, velocity, right? And speed equals delta d over delta t. Okay, so 0.9 kilometers divided by, it's still 925 seconds, equals. And so here now, I only have one significant figure. Okay, so you see the only significant figure in the top here is the 0.9, or is the 9 and 0.9. So my answer is only going to have one significant figure. And so when I do this, it's going to be 0.001. It's still kilometers per second. And now I'm going to, because it's velocity, I'm going to add my direction, which is west. Okay, so this answer, when we actually put it in the calculator, it was 0.00097, okay? And because I need it to be one significant figure, that 9 in the 10,000th place rounds up to a 1 in the 1,000th place, and it's just one significant figure. And so the velocity is 0.001 kilometers per second. Oh, and I didn't even write what I was supposed to put here. Make sure you do that. Okay. West. And I would figure that out when I go back and do what I'm about to do, is check that I'm answering what the question's asking for, right? So my first answer is the speed, answering the speed, and these are units of speed. Second answer is velocity. And oh, I see that I've highlighted that. Yes, I have a direction there. And kilometers per second, west is units of velocity. And so that's my check on that one. Okay. Number 5, a car is on a highway traveling at 25 meters per second west. A truck is on the same highway traveling 29 meters per second west. What is the velocity of the car relative to the truck? So I have 3 questions here, okay? Velocity of the car relative to the truck. Velocity of the truck relative to the car. And then if the two vehicles eventually collide, which one was ahead? Okay, so I see this word relative. I know I'm going to want to use this relative velocity equation, okay, where the relative velocity is the velocity of the first moving object minus the velocity of the reference object. So when I see relative to the truck, that means the truck is my reference object. Okay? And so in this first question, the car is going to be the moving object, and then the truck will be the reference object. In this second question, I'm just reversing that, okay? So what is the velocity of the truck relative to the car? The car is then my reference object in the second question, okay? So I'm going to label these relative v of car equals, my velocity of my car is 25 meters per second. I'm not going to write west here. Okay, I'm going to highlight here west. I see west there, and west is positive. And what you choose to be positive or negative really doesn't matter. You'll end up with the same answer anyways. So if you did this and, for example, here up here you chose opposite of which was positive or negative, you still probably got the answer right. And so the way I do it, whichever one I choose, you don't have to do exactly the same thing. If they're both the same direction, it makes sense to both be positive though. Okay, so the car velocity 25 meters per second, because it's positive, that's my designation of direction while I'm doing the equation. Okay, and so minus the velocity of my reference object is my equation. Okay, so my reference object is 29 meters per second, also positive. And so my relative velocity of the car equals 4 meters per second. So the velocity of the car is 4 meters per second relative to the truck. Okay. Then, so now my relative velocity of the truck. And it's just going to be the opposite. 29 meters per second minus 25 meters per second. Because like I said, we're just switching which one is the reference object. And that is going to equal, oh, and you know what? So I would figure this out when I go back and check. 4 meters per second, I don't have a direction here. Velocity needs a direction. And so west. Okay. Okay. So -4 meters per second here. And so now I'm going to remember it this time. The velocity of the truck relative to the car is, I'm not going to put a negative here, okay? My directionality is based on me writing the direction and when I'm doing this for the final answer. Even if you aren't doing this in sentences, you will change this negative value and kind of convert it to a directional value, okay? So the velocity of the truck relative to the car is 4 meters per second, and it's negative, so it needs to be east, okay? So now my last question, if the two vehicles eventually collide, which one was ahead, okay? And And so you can kind of just figure this in your head, right? The truck is, they're traveling the same direction, and so the slower vehicle has to be in front for them to collide, right? If the truck was in front, then it is going to always be going faster than the car, and it's in the same direction, and so there's no way that they collide. And so the the car must be in front for the vehicles to collide. Okay, and those are our answers. So now we'll go and check, right? So our first question was asking, what is the velocity of the car relative to the truck? I say velocity of car is this relative to the truck. And, you know, I would even, should have done it earlier. Whenever I see the word velocity, I'm highlighting that bad boy, okay? So the velocity, and I see that I have west there, so I'm good. All right, the velocity of the truck relative to the car. I have velocity of truck relative to the car, and I have 4 meters per second east, which is units of velocity. And then I'm answering the final question. If the two vehicles eventually collide, which one was ahead? Okay, so these questions that have multiple questions within them, make sure you're paying attention and answering all parts of the question. That is one of the #1 things that my students lose points on in questions like this, is that they don't actually answer all the questions. They're so relieved when they get the first part of the question done that they just move on. Okay. So now number 6, you are walking with a constant velocity of 1.5 meters per second north. I see velocity, I'm going to highlight it. Okay. If you walk for 15 minutes, what will be your displacement? Okay, I also see that direction. I'm going to highlight that. And whenever I see a direction, I'm going to assign it a positive or negative value. Okay, and I'm looking for displacement. Okay, my values 1.5 meters per second north and 15 minutes. Okay. So let's use our velocity equation. Velocity equals delta x over delta t. Okay, my delta x is my unknown. Okay, that's what we're being asked for. My velocity is 1.5 meters per second. I'm not going to put the north there. I've assigned it a positive value, and that's how it's going to go into my equation. So equals delta x is my unknown, and my delta t, my change in time, is 15 minutes. Now, before I move on, I'm going to double check that everything in my equation, the units match up, and they don't, right? I have 15 minutes here and I have meters per second here. So I need to do some adjustment here and convert this to seconds, okay? All right, so let's off to the side here. 15 minutes times, for every 1 minute, there are 60 seconds. Okay. And that is going to give me 900 seconds. Okay. So now that I have that, I'm going to rewrite this. 1.5 meters per second equals delta x divided by 900 seconds. Okay. And so now to get delta x, I'm going to multiply both sides by 900. Seconds. Especially as we get further along and there are lots more different units, always include your units, even in these, even in the calculation part. Don't just check it at the end and throw in the unit that it's supposed to be. Okay, so my seconds are going to cancel, right? And my final answer then, so I'm going to get with my calculator 1,350 meters. Okay, and it's positive, so that's going to be north. But I'm not done yet. Okay, I need to make sure that I'm using the correct number of significant figures. So I'm going to go back to my original values, and everything is multiplication and division here. So we need to use the lowest number of significant figures that is in any of our values that were part of the equation. So 1.5 meters per second has 2, and so does 15 minutes. And so our answer needs to also be 2 significant figures. And so I'm just going to round that up, 1,400 meters north. Okay. And so then finally, I'm going to put that in a sentence. The displacement is 1,400 meters north. Okay, and I didn't do this earlier, but displacement is a vector quantity, and so we could also highlight that with yellow. Okay. So now we're going to do question 7. You ride your bicycle with a velocity of 11 meters per second west. West, I'm going to assign as positive. If you do that until your displacement is 7.8 kilometers west, how long will it take you? So how long? Okay, my answer is going to need to be in seconds. Okay, so it's good to sometimes, as soon as you see that question, be thinking about what units you're trying to get your answer into. Okay, so I'm going to look at what I'm given and decide what equation best solves this problem. Okay, I have velocity, I have displacement, and it's asking me for seconds. It's asking me for time. And so that's easily going to go right into our velocity equation. V equals delta x over delta t. Okay. Now, earlier in question 6, I put together the equation and then I was like, oh no, the units don't match. You can also look at this beforehand, right? I have 11 meters per second west and 7.8 kilometers west. I know that's not going to fit together. I'm going to need to adjust my kilometers to be meters. Okay, so I'm going to do that first. 7.8 kilometers, and I'm just going to multiply that times 1,000 meters for every 1 kilometer, and so 7,800 kilometers. Now, if you've done this enough in other classes, including chemistry, you might be able to just automatically say, oh, that's 7,800 kilometers. But that is the equation to do it if you aren't quite as well versed in it. Okay. And so now that I have, and I just did that wrong, 7,800 meters, right? Okay. And so now that I have that converted so that we all have everything in the same units. Now I'm going to plug it in. So my velocity is 11 meters per second. West is positive, equals my delta x, my displacement, is 7,800 meters, and I am solving for my time. Okay, so the other way we can write that is delta t equals 7,800 meters divided by 11 meters per second. My meters will cancel, my second goes up to the top, and my final answer then for my delta t is, with the calculator, I'm going to get 709 seconds. But again, I'm going to look at my significant figures. Here I have 2, here I have 2. So and this is all division. So we're following the division rules for its total number of significant figures needs to stay the same. And so I need to change this to 2 significant figures. So I'm going to change that to 710 seconds. Okay. And now changing that to a complete sentence, it will take me 710 seconds. And you can just leave it at that. It will take me 710 seconds. Okay. So now let's check everything. How long will it take you? This is a unit of time. And I said how long it would. Now, time is not a vector value. Okay. So even though I have all this highlighting, I have to know that time is not a vector value. Vector quantity, I should say. Velocity is, and displacement is. But those end up canceling out and we're left with seconds. And seconds, we're not going to say it's going to take me 710 seconds west, right? That wouldn't make sense. So this is just fine the way it is, and we don't need to do anything with the west. Now, if the values here were different, like if one was west and one was east, which it would be a more complicated problem, then you would definitely have to do something with the positive, negative, and things while you're doing the equation. But answer is in seconds, so not a vector quantity. Okay, question 8. 2 cars start next to one another on a road. One travels at 31 meters per second north, while the other travels at 28 meters per second south. Okay, so we have 2 different velocities, and they're going different directions. How far will they be from each other in 22 minutes? Okay, so this how far will they be from each other? This is not a vector quantity, right? Isn't there? It's just going to ask the distance apart they are from each other. So I can already look ahead and say, okay, my answer is not going to have this north-south, but you can bet this north and south is going to come into play. Okay. I tend to just always assign the first one I see positive, and you can do something different if you want, but that's how I'm going to do it for this example. Okay. And so I have 31 meters per second north, I have 28 meters per second south, and 22 minutes. Okay. So the only equation that I have so far that has 2 different velocities is my relative velocity equation. And so that makes a lot of sense to use right now. We're going to see what is the distance, what is the difference in the velocity that they're traveling, and then we'll be able to use the time. Okay. So we're just going to say the relative velocity of car A. We'll call this car A. And this one is car B. Okay. And so relative velocity equals my car A is traveling 31 meters per second. North is positive, so I'm just not going to do anything there and just leave it as 31 meters per second. Okay. And then it's going to be minus my velocity of my reference object. Okay, so my reference object is B, and so it's minus a negative, and so it's going to be positive. Okay, 28 meters per second. Okay, so I'm subtracting negative 28 meters per second, same thing as adding it. And so my relative velocity equals 59 meters per second. Okay, so they're starting next to each other and they're going apart from each other at a rate of 59 meters per second. Okay, so now I have this, how fast they're moving away from each other value. This is the velocity, and I'm given time, and I want to find the distance. And actually, we could say that this is distance, right? So like if this is relative velocity, car A is traveling 59 meters per second north away from car B relatively. Okay, but because we are just trying to get distance, that direction value doesn't mean anything to us right now. All right, so we're just going to use this as a unit of speed rather than velocity. And that's the way it's written right now, just speed. Okay, so my speed equals my change in distance divided by my change in time. And so this delta D is what I'm trying to get. So my speed is 59 meters per second. My delta D is unknown, and my time is 22 minutes, right? And so as I'm verbalizing this, I see second, and then I looked at that and said minute. So let's do a conversion. 22 minutes times 60 seconds per minute. And that equals 13. So this is 1320 seconds, but I need to keep this the same number of significant figures, okay? So I had 2 significant figures here, so 1300 seconds, okay? So that's what I'm gonna plug in here now. 1300 seconds is my time. Okay, so now multiply both sides by 1300 seconds. Seconds canceled, then I'm left with meters, and I am ultimately get, move this over here. So my calculator output is 76,700 meters, but I'm going to look at my significant figures, right? I have 2 significant figures, 2 significant figures, 2 significant figures. So I definitely need to get this into 2 significant figures, and so it's going to be 77,000 meters as my answer. Okay, so my final sentence answer is the cars will be 77,000 meters apart. Okay. And for the sake of whoever is grading these, it's always good to, I haven't been doing it, but always good to just box your final answer, and that is what they're grading. So ignore like this box here. Okay. Okay, number 9. A car is traveling at a constant velocity. Is there a net force acting on it? How would your answer change if you only knew it was traveling at a constant speed? okay? So I'm not going to write this out. I'm just going to sit here and explain it. Okay, so net is the key word here. Like, I'm sure you're thinking, but I have to hold the accelerator down to achieve that constant velocity. And so there's a force I'm applying, right? But the reason that you have to hold that accelerator down when you're driving that car is because of friction. And friction is a force that is resisting the motion. And the engine that is propelling the car is overcoming that friction, okay? So without the friction, if a car was traveling at a certain velocity, no force would be needed to maintain it. You would not have to press on that accelerator more than that initial time to get it to the speed, the velocity that it was at. And that's based on Newton's first law of motion. And the force of but when we are actually driving a car here on Earth, the force of the car's engine is canceling out the force of the friction. And so therefore, when it's traveling at that constant velocity, the net force at that time is 0. Okay, so our answer here is that there is no net force acting on the car. Now, if all we know is that it's traveling at a constant speed, there may or may not be a net force acting on it. And what's going on there is that it depends on the direction, right? So if the car is changing direction but staying the same speed, then there may be a net force that is acting on it, okay? And that's the answer for number 9. Okay, question 10. A man is riding a horse with a constant velocity when suddenly the horse plants its feet and stops. When that happens, how will the man move relative to the horse? And I'm sure that you can imagine how this man moves relative to the horse. The man is going to move forward relative to the horse. And that's because the man still has the horse's original velocity when the horse stops. So, unless he is exerting a great amount of force on the saddle to prevent it, he will keep moving forward when the horse stops. Question 11. You are told that object A has much more inertia than object B. If they are both traveling with the same velocity, which will be harder to stop? And so if A has much greater inertia, then it has the tendency of a body to resist changes in velocity. That's what inertia is, the tendency of a body to resist changes in velocity. So it has a greater tendency there. And so therefore, if object A has more tendency to resist changes in velocity, then it will be the one that is harder to stop. So object A will be harder to stop. Number 12, a moving object is experiencing a net force. Is it accelerating or not? Well, from what we did up here, if there is no net force, then the velocity stays the same. So therefore, because there is a net force acting on this object, the object's velocity is changing. And the definition of acceleration is that the velocity is changing. So yes, for question 12, this moving object is accelerating. Question 13. Okay, so we're referring to this graph here. At what times does the object in the graph experience an acceleration? What direction is that acceleration? So, key thing here has to do with our directions. Positive is east in this graph. Okay. Okay, so an acceleration means that the velocity changes, right? So here, this velocity is constant. It's a nice straight line. And then at 4 seconds, the velocity increases. So it's going faster east. Okay, so 4 seconds is a change in velocity, which is defined as an acceleration. Okay, so I'm going to start writing this out. The object accelerates at, and we're going to estimate this to whenever we have a graph like this, we want to estimate to 1 digit more than what is shown, right? So we have the ones units, so we're going to estimate it to the nearest tenth, okay? And so this is going to be 4.0 seconds. And then, so where else does the velocity change? Velocity is constant, constant, constant. There is a change here. And so 8 seconds, there is an acceleration. The velocity changes. Okay. At 10 seconds, we see another change in the velocity. Okay. So those are all the times that the object experiences an acceleration. What direction is that acceleration? So at 4 seconds, the acceleration is east. Okay, and that's because the slope is increasing. Okay, we're going faster east. At 8 seconds, the acceleration is west. Now, how we know that is if the velocity increases, then your acceleration is going the same direction as what the velocity is going. If the velocity decreases, your acceleration is going the opposite direction. And so this velocity, the slope is higher here than here. And so here the slope is 0. And so your acceleration is west. At 10 seconds, the acceleration is also west. The slope drops even further, and so therefore your acceleration is west. Okay. So now question 14, during what time interval is the object not moving? And so for this, we're going to be looking for the velocity. So let's come back and look at what these measurements are. We have time and position, right? And so velocity is defined as the change in position divided by the change in times. And so it's simply the slope of this graph at any point is the velocity. Okay, so the rise over the run. Okay, so here we have a positive slope, so that is a positive velocity. Positive slope, positive velocity. From 8 to 10 seconds, the slope is 0. And so that means the velocity is 0, which would of course mean that it's 0 meters per second and the object is not moving. Here from 10 to 20 seconds, that slope is negative, and so it's moving in the opposite direction, in a westerly direction. Okay, so I'm not going to write the answer here because that's pretty simple, but from 8 to 10 seconds, and you would say 8.0 to 10.0 seconds. Remember that we're always going to estimate 1 unit further than what our marks are. So 8.0 to 10.0 seconds, the object is not moving. Question 15. During what time interval is the object east of its starting position? Okay. So it is moving east, all right? And so we know for sure that when that slope is positive, it is definitely east of that position since it hasn't ever gone west before, right? So starting at 0, it is east, and then it stops, and then starting at 10 seconds, it starts to move west. And we need to look at what position it is now becomes west of the starting position. So we know when that easterly position stops. Well, our y axis here tells us what that position is, all right? So 0 is the starting. We are east, east, east. Anytime that we are positive, we are east. And so we stay east until right here at 16.0 seconds. And so for this answer for 15, the object is east of its starting position from 0.0 to 16.0 seconds. Okay. Then the next part of this, for what time interval is it west of its starting position? So again, we're just looking at the position here. And so starting at this point, at 16 seconds, it's going to be a negative position, which means that it is west, since positive is east. So the object is west of its starting position from 16.0 to 20.0 seconds. Okay. Question 16. Are the instantaneous and average velocities from the same are the instantaneous and average velocities the same from 2 to 6 seconds? And then it says, what about from 14 to 18 seconds? Okay. So from 2 to 6 seconds, we have 2 different velocities. And the reason we know that is because the slopes here are different, right? From 0 to 4 seconds, we have one slope. And from 4 to 6 seconds, we have another slope. And so at any given point, we might have 2 different slopes at, say, 3 seconds versus 5 seconds. And so this question is asking, are the instantaneous and average velocities the same from 2 to 6 seconds? Well, that answer would be no, because our average slope here is going to be different than at any given point than the instantaneous slope at any of these points, okay? Because we have 2 different slopes there that we would be averaging. Then from 14 to 18 seconds, okay? Notice it's not asking us to calculate these. It's just asking if it's the same. So from 14 to 18 seconds, we have one constant velocity. This is a nice straight line, which means that velocity is constant. We can, if we needed to, we could determine what that velocity is by determining what that slope is based on values along this line. Okay, and so because this is one constant slope, one constant velocity, yes, the instantaneous and average velocities from 14 here to 18 seconds are the same. Okay, now 17 asks us, what is the instantaneous velocity at 1 second? So now we are being asked to determine that. And so at 1 second here, 1 second here, we're going to determine what that slope is. So we can take values anywhere along this line that is all the same slope and velocity to determine what that instantaneous velocity would be. Okay. So let's, and we're going to have to estimate this because none of these are on exact points. So if as you're doing this and checking your work, if your estimate is 1 or 2 meters or seconds or tenths of a second, 1 or 2 meters or 1 or 2 tenths of a second off, then what I have, that is okay because this is an estimate. Okay, so I'm going to use the point here where, and this is a nice easy one to use, where my time is 0 and my position is 0. So that's a nice easy one to use for my calculations. And then I'm going to go ahead and use the value that is at 4 seconds. And I'm estimating that the position at 4 seconds is about 8 meters. Okay. And so I'm just going to be calculating the slope there. So 8 meters minus 0 meters. So that's my rise. All right, you take the second point minus the first point, so 8 minus 0. And then for my run, I'm going to say 4.0 seconds. And remember, I'm estimating one more decimal place further. Okay, 4.0 seconds minus 0.0 seconds. Okay, and so that simplifies quite easily. This is why I use that 0 point, because it's just going to be 8 meters divided by 4.0 seconds. Okay, notice, so now for significant figures, I only have one significant figure in this 8 meters. I can't go any further than that because this, these position grid marks are to the nearest 10. And so the most I can estimate is to the nearest 1. Okay, 1's digit. So 8 meters over 4.0 seconds, I'm going to have one significant figure in my answer. And that's going to equal 2. I'm not going to put 0.0 because that would be more than one significant figure. And my units, of course, are meters per second. And I didn't go back to this, right? But velocity is a vector quantity. And so I need to put the direction, right? And it's this is positive, right? So it is going east. 2 meters per second east. Okay, and so the instantaneous velocity at 1 second is 2 meters per second east. Okay. All right. So move on to question 18. An experiment has only random errors in it. One student performs it 10 times and averages her results. The other does it just 1 time and reports the result as his final answer. Most likely, which student will be more accurate? Okay, and so this goes back to the discussion in the chapter about random error and how many replications that you should do in an experiment. And so the more replications that you do in an experiment, the less that random error becomes a factor. Because let's say, I'm going to just kind of draw down here. So let's say your true value is right here, okay? And with random error, what you'll have is if you have 10 replications, you might have one of them that ends up right here, one right here, 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 right, and so on. And so ultimately, the average of this will be closer to what the true value is, will be close. The more replications you have, the closer your average will be to the true value. Versus if you only have one replication and the true value is, say, right here, if in that one replication, let's just say you got this one, right, down here, you are not as accurate to what the true value is. And you might get it right here, but you have a better chance of, and from that one replication, you might get the true value, but you have a better chance of getting close to that true value with an average of more replications than you do if you only did the experiment one time, okay? And so our answer here for question 18 is that the student that performed the experiment 10 times is going to have more accurate results than the student that only performed it once. Okay. For question 19, it asks us, how would our answer to 18 change if this experiment had systematic errors in it? And the answer to that is simply that it wouldn't really matter. So systematic errors mean that there is a problem in how you even performed your experiment, okay? It's not just random error that is due to things that we can't control. A systematic error is something that you could control, but you did the experiment incorrectly, okay? And so if that is the case, doing more replications isn't going to help you, because these errors are going to insert a variable that is automatically going to change the result away from the more accurate, towards being less accurate, okay? And so if the experiment has systematic errors, then it wouldn't matter whether we do the experiment 10 times or one time. Those errors will introduce an error that is not overcomable by doing more replications. Okay? So averaging does not help with systematic errors. So that is the end of the review questions for Chapter 1. If you have any questions, feel free to leave them in the comments, and I or maybe somebody else can help you.